This is Tim O'Brien in Seattle. This is part 2 of a series on databases and the emergence of vector databases. If you're just joining us, I'd strongly recommend starting with part 1, where I lay the foundation for understanding how we got here. From the days of Oracle-dominated shops with dedicated DBAs to today's polyglot persistence chaos. This series is all about understanding the dramatic transformation in how we store, manage, and think about data over the past 3 decades, and why these changes matter for anyone building software today. And for a quick recap of part 1, I told you about a DBA that I used to work with in 1999 and how different the world was back then, how protective all companies were of usually the single relational database that ran an entire organization. We explored 3 major shifts that really removed DBAs from day-to-day developer experience. The first shift was the explosion of choice. We went from 28 known database systems to 426 databases. That's a 15x increase, driven by specialized needs for different types of data at scale. I then talked about the cloud revolution and how the emergence of the cloud took away operational responsibilities that required a DBA to be present. I then talked about how languages, programming languages, started to get smarter around how they used a database. And lastly, we looked at the staffing numbers. We looked at the developer to DBA ratio, which was 6-to-1 in the year 2000, and 12 or 22-to-1 in 2023. This means that developers are now responsible for the databases, and there are more databases to be responsible for. We gained speed, elasticity, and choice, but we also lost institutional wisdom that came with having a DBA available. Today, in part 2, we're going to talk about vector databases, and these aren't just new databases. They're a whole different way of thinking about data. If you go back to 2004 or 2008, with the switch to NoSQL databases, we were still dealing with records that were stored in databases. But today, with vector databases, these databases store something fundamentally different. They're databases built for a world where artificial intelligence turns everything into numbers, where meaning itself becomes an abstract geometrical quantity, and where the questions we ask our data have shifted from what matches this criteria to what's similar to this concept. And I want to be clear, even though you'll hear me talk about things like Milvus or Postgres in this episode, I'm trying to stay as far away from specific products and technologies as possible. And I'm doing that on purpose. There are a lot of people that work with databases, and not all of them are programmers or DBAs or system administrators. In this episode in particular, I'm going to step back and explain as much as I can, because one of the goals in this episode is that non-technical listeners have a chance of understanding these topics. Non-programmers understand databases, and while they might not understand composite keys or inner joins, most people that have used a computer understand that a database has rows and keys. Where possible, I'm going to try to explain a vector database to that audience, while also providing some fundamental context for working developers. But this episode is also for working developers, working system administrators, and working DBAs. I'm about to give away one of your secrets. If you've been in an IT department over the last 3 years, you've been in meetings where the majority of attendees are nodding in agreement, like they've been using vector databases for a decade. They haven't. You've also been in meetings where people are like, oh, generative AI, of course. A lot of people pretend. I'm not calling that as a bad thing. It is just a fact of life. So if you're a developer and you're now responsible for one of these vector databases, but you really don't fundamentally understand how they work, what algorithms are there, how the data is stored, this episode is also for you. So let's dive right in. This new complexity, it's vector databases and the AI gold rush. If you think the explosion from 28 to 426 database systems was dramatic, the next turn of the wheel is weirder. Vector databases. Instead of just storing rows and JSON objects or documents, they store numerical fingerprints that fall out of modern machine learning models. Embeddings. If you've been using a large language model for the last few years, and who hasn't, you've probably heard about fine-tuning and vector search. These are different but complementary approaches. Fine-tuning updates a model's weights so it behaves differently, while vector databases store embeddings of your data so an LLM can retrieve relevant context at query time. Many teams use both fine-tuning for specialized behavior, vector storage for dynamic knowledge retrieval, Every bit of content, every piece, every document, every domain-specific fact can be encoded into what are called high-dimensional vectors, and these need to be stored, indexed, and retrieved at lightning speed. So text embedding is the process of converting text into numerical vectors that capture semantic meaning. It's how we translate human language into the mathematical space where AI models live and breathe. OpenAI's text embedding ADA-002 became the de facto standard for many teams because it hits a sweet spot. It's fast, it's relatively inexpensive at scale, and produces a 1536-dimensional vector that are expressive enough to capture nuanced meaning while being computationally manageable. When you feed it a paragraph of text, it doesn't just count words or match keywords, it encodes concepts, relationships, and context into a dense numerical fingerprint that similar text will share. Now, if you look at this text embedding ADA-002, when you send it a paragraph, it tokenizes the text into subword units, it processes them through a transformer-based architecture, and it outputs a single point in a 1536-dimensional space. OpenAI hasn't published the specific training objectives, but we know it's optimized to capture semantic relationships between texts. And I want to be clear, this is a model. It's not like the 1536 dimensions have meaning. It's not like someone coded something to say, oh, well, if it's about this, then this dimension is going to have this value. No, it's a model that has created a 1536 dimensional space. It's a series of numbers, and you store it in a vector. So the same trick also works for images. A vision model starts with a grid of pixels. It pushes it through a convolutional layer or a vision transformer, and then it collapses all of that into a high-dimensional vector. Common sizes include 512 for something called clip, or through some modern pipelines, they'll use 256 via a truncated or compact model. Those dimensions collectively encode edges, textures, shapes, colors, and object parts in combinations the model has learned during training. In that sense, an image really does become a point in a multi-dimensional vector space, and similar images are simply points that land close together. Traditional databases excel at exact matches and range queries, find all the orders where customer ID is 123, or get all the products where price is less than 50. But embedding models operate in this high-dimensional geometry. When text embedding ADA-2 converts text into 1536 floating point numbers, or a vision model converts an image into a 512-dimensional vector, the classic indexes break down. B-trees, what we use to create indexes on relational databases, they weren't designed for find the 10 most semantically similar documents to this query. So what you need to know about these databases is they're doing a completely different thing than the databases you're used to using. They're comparing these multi-dimensional vectors to each other, they're calculating distances, and from that, via the magic of generative AI, which I'm not going to go into in full detail here, they are able to allow us to gather some semantic meaning from text and compare that to other text and to derive tokens when we're generating tokens in a large language model. The financial explosion around this technology tells the story better than any technical explanation could. Generative AI spending was barely a blip in 2022. Most enterprises were still experimenting with ChatGPT in their browsers. Fast forward to 2025, Gartner projects worldwide spending on generative AI will reach $644 billion, with a 76.4% increase from 2024 alone. And that's not just growth. That's an entirely new economy being built on vectors and the databases that store them. As important as graphics processing units, GPUs, are to the execution of these large language models, vector databases play an expensive supporting role. Every Retrieval-Augmented Generation, RAG application, every semantic search feature, every AI-powered recommendation, they all need somewhere to store and retrieve their vectors. And they need to do it at a scale that would have seemed impossible just 3 years ago. Enter vector databases. They're built from the ground up for similarity search in high-dimensional space. And suddenly, everyone needs one. So let's take a little bit of a step back and talk about what is a high-dimensional space. When I say that text embedding ADA002 maps a paragraph into 1536 floating point numbers, that's not a number I made up. That's the actual fixed output size of that model. You can think of that output as a coordinate in a 1536 dimensional space. The same way a point on a map might be latitude and longitude in 2D, or a point in a 3D game might be X, Y, Z. A high dimensional space is just what happens when you keep adding more coordinates. So why so many dimensions? Because meaning in these systems is emergent. It's not hand-designed. Each coordinate is just a learned number. There is no, this access is database and this access is sarcasm. If you crack open an embedding vector, you won't find a music preferences slot or a likes to program in Rust flag. What we perceive as structure, topic, style, sentiment, even something like musical taste, it comes from how points arrange themselves relative to each other after training, not from any one dimension having a clean, human-readable label. And I just want to emphasize the word emergent. That emergent structure is part of what rattled people when large language models started surprising their creators in the early 2020s. A model trained to predict the next token on enough text suddenly showed the ability that it wasn't explicitly programmed for. It could translate language. It could help with coding. It could answer questions. And I want to be clear, there's no it there. There's just a collection of numerical vectors that represent knowledge and the relationships between those vectors. But as Wei and authors put it in their 2022 paper, Emergent Abilities of Large Language Models, some capabilities appear unpredictably as a byproduct of increasing model scale. You don't build a sarcasm module. Sarcasm-like behavior just shows up because of the geometry of this space, shaped by vast training data and mind-bending amounts of compute. The things that we're now using every day emerged. And just a personal note, before ChatGPT 3.5 broke, a couple months before that happened, I got a call from a colleague of mine who worked at a company I won't name. And he told me about these models that they're training and working on and how they're freaking people out. This was, again, I think, maybe late 2021, early 2022. He was telling me that they had trained a model and they had given it all of the data about the employees in a particular company, and it was correctly predicting who was about to quit in ways that were surprising everyone. And I want to emphasize, I'm not going to tell you where this person worked or what their name is, but what it left me with months before the OpenAI news broke was something was happening. Something was happening that was freaking the people out who were in charge of these models. And so when I think of the word emergent, that's what I think about. I think about people working on these generative AI models, and suddenly, because they reached a certain threshold of knowledge, of complexity, they started to be able to ask questions and have those questions be answered. And what I'm trying to get across here is that emergence, that knowledge, it's a byproduct of what this vector is capturing, the high dimensional space that is encoding knowledge or sentiment or sarcasm or shape or anything. That high dimensionality is what makes the geometry expressive enough to capture meaning. And I want to be clear, it's not capturing meaning as much as it's representing meaning, knowledge, concepts, color, shapes, emotion, intent. With hundreds of thousands of dimensions, the model has enough room to place two sentences that look different on the surface, but mean the same thing very close together, while shoving genuinely different ideas far apart, often in directions we can't name, but the model can reliably navigate. That's also why the training runs behind these models that chew through staggering compute budgets, measured in billions or trillions of gradient updates, and cumulatively exaflop scale workloads. You're effectively sculpting the shape of this huge, invisible space so that the right meanings end up near each other. This is also why it's basically impossible to visualize in any faithful way. In 2 dimensions, you can literally draw clusters of related points. In 3 dimensions, you can still sort of picture them as clouds. But in 1536 dimensions, almost all the volume lives near the edges of the space. Most points are far from each other, and the geometry starts to behave in ways that feel alien. This is what is called the curse of dimensionality. It's the same problem popular science books ran into trying to explain string theory's 10 dimensions with rubber sheets and garden hoses. These analogies are cute, but they leave you with a misleading picture. With embedding spaces, trying to imagine actual 1536 dimensional shapes usually does more harm than good. So my advice here is to stop thinking about shapes and geometries or drawing this on a graph. It's better to think about distance and angle. And again, try not to think about this on a chart. In 2 dimensions, you'd calculate the distance between 2 points by looking at the differences along the x and y axes and combining that into a single number. In 1536 dimensions, you're literally doing the same thing in principle. You're aggregating 1536 coordinate differences into one similarity score. But the arithmetic is gnarly, and this is why we need so much compute. This is why we're spending so much on GPUs. So there are 2 things to know when it comes to vector databases. One is called cosine similarity, and this treats each embedding as an arrow from the origin, and it asks, what's the angle between these arrows? 2 vectors pointing in nearly the same direction, again in a 1536 coordinate space, are treated as semantically similar, even if their raw magnitudes differ. And again, I want to simplify this, but I also want to remind you that you're in a 1536 dimension space. An arrow pointing at a specific coordinate has a lot of different angles, if you will. And so what's happening here is you're literally measuring if 2 vectors are in the same direction. That's a way to oversimplify something that is fairly complex. And because the exact distance checks against every vector in a billion-point index would be unbearably slow, vector databases then lean on what's called an approximate nearest neighbor, or an ANN. This is an algorithm that builds a graph or clustering structures that let them quickly find points that are probably among the closest. It trades a little bit of accuracy for huge wins in speed and cost. But the thing to know about vector databases is, let's say you throw a billion vectors into a vector database, and you're trying to fine-tune an LLM, or you're trying to say, what's semantically closest to this phrase? That's not going through and comparing it to all billion vectors. It's using cosine similarity and approximate nearest neighbor. There's a bunch of different strategies here. We'll touch upon some of them later in this episode. But this is a whole new way of thinking, right? For most of human history, we've treated information as something that lived in sentences, in books, in laws, discrete artifacts that you could point to and say, that's where the meaning is. Vector databases and models built on top of them quietly argue for something stranger, that meaning can be smeared out across huge mathematical space, that understanding can show up as distances and angles between points in a geometry we can't even imagine. When people talk about GPT, generative pre-trained transformer, or BERT, bidirectional encoder representations from transformers as breakthroughs, they are right. But I think the deeper innovation sits underneath those acronyms. It's this realization that you can encode concepts, relationships, metaphors, styles, everything from Enlightenment-era political theory to Snoop Dogg's laid-back bravado as locations and directions in a high-dimensional space. And then you can reliably navigate that space with math. And so as much as you're hearing about OpenAI and Anthropic and all these wonderful companies, the thing that shocks me the most about this revolution that we're in the middle of is that I can download Llama from Meta, and I can run it locally, and I can ask it, in what year did the French Revolution start? It doesn't have that knowledge in it. It just has vectors that have been encoded, and it's calculating the semantic space using some of the mathematical concepts that I've explained in this section. I don't know about you, but that still freaks me out. So when you ask ChatGPT 5.1, how would Snoop Dogg say, we hold these truths to be self-evident, that all men are created equal, and that they're endowed by their creator with certain unalienable rights, and that among these are life, liberty, and the pursuit of happiness? And ChatGPT 5.1 responds with, all right, check it. These truths be clear as day. You feel me? Every last one of us come into this world equal, blessed up by the creator, with rights you can't snatch. Life, liberty, and the whole pursue your happiness vibe, for real. That's using cosine similarity, an approximate nearest neighbor, to navigate multiple centuries of cultural knowledge. and create connections between the two. And so fundamentally, when you're using a vector database, what I'd like for you to realize is that you're finding a way to help store semantic meaning, knowledge, in a way that enables large language models to work. I find it fascinating. So what's happening behind the scenes is a lot of calculation. Once you see it that way, vector databases stop being just another back-end technology, and they start looking like a primitive, early attempt to create a new kind of library. A library where there are no shelves, there are no sections, there's no labeled aisles, just a continuous space in which Jefferson and Snoop Dogg and self-evident truths are all approximate nearest neighbors. It's a fairly weird world that we live in. But hopefully, this section has made vector databases a little more intriguing if you weren't aware of this. So it's not just text embedding ADA002. I've been picking on OpenAI's model because it's clean. It's a concrete example of a 1536 dimensional space, but it's just one point of a much larger design space. Newer OpenAI models like text embedding 3 large push the default dimensionality up to 3072 dimensions, but they can also be configured down to a few hundred dimensions. Microsoft's Azure SQL team shows it running effectively with as few as 256 dimensions, and when you're willing to trade a bit of accuracy for efficiency, other families go in different directions. Gina's Embeddings v3 ships with 1024 dimensions, and it explicitly supports a way to truncate vectors to 512, 256, and even 32 dimensions with surprisingly small quality loss. Popular open source models like all mini-LM L6v2 live comfortably down to 384 dimensions. I just threw a bunch of acronyms and project names at you. I'm not expecting you to go look those up. What I'm trying to get across is that 1536 dimension number from the ADA model, that's just an arbitrary number. That's just the first model that everyone started using. Different models are going to have different dimensions. Lower dimensions are going to be cheaper. They're often good enough. And what you're finding recently is we're starting to move towards models that are being designed with fewer dimensions. And those same models are starting to use fewer bits when they represent floating point numbers. And this is leading to much faster execution. The next question might be, why vector databases? Why now? Here's what's changed. Large language models made semantic understanding cheap. Before 2022, encoding text into a meaningful vector required specialized models, careful training, and deep natural language processing knowledge. Now, one application programming interface called OpenAI, Anthropic, or your preferred provider, that gets you an embedding. And every piece of your text in your system can become a searchable vector. The use cases of this exploded overnight. Semantic search. Forget keyword matching, find documents about database performance, returns results about query optimization, indexing strategies, and capacity planning, even if they never use the word performance. Recommendation systems. Users who liked this vector also liked this vector. Netflix and Spotify have done this for years. Now every app can. RAG applications. The killer app of 23-24 was to take your company's knowledge and store it as vectors, find the relevant context for each query, feed it to an LLM. Suddenly your chatbot knows about your specific products, policies, and procedures. Anomaly detection. In high-dimensional space, outliers stand out. Fraud detection, security monitoring, quality control, all vector problems now. Deduplication. Find similar content across millions of documents, critical for content platforms, legal discovery, and research. But here's the thing that keeps me up at night. We're repeating history. Just like developers in 2009 reached for MongoDB for everything, I see teams throwing vector databases at problems that don't need them. Exact matches are still faster in Postgres. If you can solve it with a traditional index, you should. Vector search is powerful, but expensive. Each query might touch thousands of vectors. Each comparison involves hundreds of floating point operations. There's also a hidden complexity. Vector databases hide enormous complexity. Those 1536 dimensions, that's a space so vast that our geometric intuitions break down. In high dimensions, everything is far from everything else. This is the curse of dimensionality. Traditional database concepts like nearby become statistical rather than geometric. To make this usable, vector databases lean on approximate nearest neighbor algorithms. Instead of scanning every point to find the mathematically perfect nearest match, they use clever shortcuts to find almost the same answers, orders of magnitude faster. That's the trade, a small loss in exactness for a huge gain in latency and cost. The main approximate nearest neighbor algorithms are HNSW, hierarchical, navigable, small world. This builds a multi-layer graph over your vectors. At the very top, you have a very coarse graph that lets you hop quickly into the right region of space. At lower levels, the graph becomes denser, and you refine your search among close neighbors. This is widely used in engines like Milvus, Qdrant, and Weaviate because it offers an excellent recall with low query latency, especially when your dataset is mostly append-only or changes slowly. The next is IVF, Inverted File Index. This takes a clustering approach, partitions the vector space into regions. Think Voronoi cells learned by something like k-means, and stores for each region a list of vectors that belong there. At query time, you only search within a handful of the closest regions instead of everywhere. IVF is useful when you need to handle very large data sets efficiently, and you can tolerate approximate results. It's also good if you want more control over the trade-off between accuracy and speed. You can tune how many regions you probe, and you tune that trade-off yourself. The third is locality-sensitive hashing, LSH. And this uses randomized hash functions designed so that similar vectors are likely to land in the same buckets. Instead of building a graph or explicit clusters, you compute these hashes and look up candidates in matching buckets. LSH shines when you have extremely high dimensional data, streaming or frequently updated workloads, or when you want a simpler indexing scheme that's easy to distribute. However, it's worth noting that LSH can require very large indexes for high recall in high dimensions. The curse of dimensionality, the fact that everything is very far away from each other with that many dimensions, hits LSH particularly hard. It often requires many hash bits to maintain accuracy. I probably lost a few of you in those three sections, but each of these algorithms is answering the same question. What is close to this vector? But with different assumptions about data size, update patterns, and how much approximation you're willing to accept. Choosing between them is as much an operational decision as a theoretical one. But then there's the operational complexity. How do you back up a billion vectors? How do you do version embeddings when your model changes? And what happens when OpenAI releases the next text embedding ADA 003 or some other new model? All of your vectors are going to need recomputing. And what that means is that you may have to recalculate some of these structures that allow you to get the approximate nearest neighbor. So that was a lot to explain. But I think what I'm trying to get across is there's a lot going on in a vector database. There are a lot of new acronyms you need to learn, a lot of new algorithms that you're going to need to understand. You might not need to write the algorithm from scratch, but you should understand what the different strategies are to calculate the approximate nearest neighbor. And what this means for the craft. Vector databases are new. They represent a logical conclusion of database specialization. We've gone from one database for everything to the right database for each data type to purpose-built engines for native AI applications. It's progress, but it's also complexity. And if there were a DBA starting today, that person would need to understand not just B trees and transaction logs, but approximate nearest neighbor algorithms, embedding models. The surface area of database knowledge, it hasn't just grown, it's exploded into multiple dimensions quite literally. So you now need a PhD in several areas just to understand what your vector database is doing, but then also how to relate that to new operational concerns that are emerging every 6 months. How do I run my vector database on a network without melting a network switch? So there are so many operational concerns about vector databases, and we've just touched the surface of what these concepts are. We haven't really fully dove into how they work. What are the different ways you can configure a vector database? What are the different options? That's what we're going to talk about in part 3. But what I have tried to convey in this episode is the fundamental data that you're storing in a vector database. What is a vector? It's a high-dimensional space. How do you query it? Query really isn't the right word. More like, how do you find the closest neighbors? How do you calculate its approximate nearest neighbor? How do you look at cosine similarity? Those are really the questions you're going to be asking yourself if you are working with a vector database. So now that you understand some of the core concepts, why they matter, why, in my opinion, they're mind-blowingly revolutionary, it's time to get practical. In part 3, we're going to dive into the actual landscape of vector database solutions that are available today. We'll explore the open source champions like Milvus, Weaviate, and Qdrant, each with their own strengths and philosophies. We're going to talk about the managed services, how Pinecone became the just make it work option, and why that matters. We're going to talk about traditional databases launching a counterattack, Postgres, MongoDB, and others scrambling to add vector capabilities. We're going to talk about that convergence play, why graph databases plus vector search might be one of the killer combinations. And then we're going to talk about the brutal economics, what it really costs to store and search billions of vectors. And just a quick spoiler, it can be pretty expensive. Most importantly, we're going to give you a decision framework, because while everyone wants to build the next ChatGPT, not everyone needs a billion-scale vector infrastructure. Sometimes Postgres with pgvector is all you need. Sometimes you do need the big guns. So part 3 will help you figure out which camp you're in. If you're tasked with choosing a vector database for your organization, or if you're just curious about what options are out there, part 3 is where we get into the nitty-gritty of actual implementations, benchmarks, and trade-offs. So if you have found yourself suddenly responsible for a vector database, I hope that I've started to let you know about some of the core concepts. It's the next episode where you're going to start to learn what your options are.